Hello and welcome to this short proof video where we're going to prove that sin² plus cos² is equal to 1 for all theta elements of the real numbers. So to do this, we're first actually going to have to redefine what we mean by sin², cos², because most of you have probably been introduced to sin² and cos² in this format. You've been drawn this triangle like this, triangle like this, right angle triangle, and then your teachers probably label these 3 points as, let's say, A, B, C. They probably label this angle as theta. They told you that this angle side opposite to the angle theta was the opposite side, the other side was the adjacent side, and the longest side was the hypotenuse. And then they probably told you that sin² is equal to opposite divided by hypotenuse, cosine theta is equal to adjacent divided by hypotenuse, and tangent of theta is equal to opposite divided by adjacent. Now this is an alright definition, but we have an inherent limitation here. This is only true, this triangle thing is only true for theta, which is greater than 0, of course, inclusive, or less than 90 degrees. Because for angles greater than 90 degrees, you get a situation that looks like this. You get a triangle that's not actually a triangle. On this side, 90 degrees here, but on this side, this angle now has to be greater than 90 degrees. So in reality, it will look something like that. And there is an interpretation. You can think like there's this imaginary line that's going in the reverse direction, coming and connecting here. But that's kind of ugly. So instead of that projected line idea, we'll instead redefine sine and cosine to make this whole proof easier. So we'll redefine sine and cosine using the unit circle. If we take this unit circle, which I'm going to draw in a second, if we take the unit circle and the x-axis, and then we consider an angle rotated from the x-axis in the anticlockwise direction. So we say we have some direction. Let's draw it properly with a line. Say we have some angle like this, and then we say that this angle rotated from here to here is theta, and we define, instead of by a triangle, we redefine sine and cosine as the coordinates of the point here, where we intersect the circle, the unit circle, at this other direction, which is an angle theta rotated in the anticlockwise direction from the positive x-axis. So that therefore this point here is cosine theta, sine of theta. So in this case, we have a new different definition for sine and cosine. Instead of having our previous definition of the triangles opposite adjacent, we still have a triangle, except this time the triangle is fixed within a circle, and the point on the circle is what actually influences sine and cosine. So here, this now allows us to find the sine and cosine of angles greater than 90 degrees. If we draw a circle like this, and we draw an angle which is greater than 90 degrees, let's say we draw a circle, draw this, and then we draw an angle like this. This angle is clearly greater than 90 degrees. So this is x, this is our given direction, and this point here is still cosine theta, sine theta, where theta is this angle. So we can actually still find a triangle here to solve for. If we construct this 90 degree angle at this point, this extra angle here will be 90 degrees minus theta, and we still have our right angle triangle here, which means we can find this point, this cosine theta, sine theta, based on the known 90 degree right angle triangles definitions of sine and cos. So we can write this angle here is pi by 2, is actually not pi by 2 minus theta, is theta minus pi by 2, theta minus pi by 2, And then now that we have an angle which is in between 0 degrees and 90 degrees, we can use the old definition of sin theta and cos theta to calculate the values of the new definition of sin theta and cos theta. We can draw the triangle such as this, where now we have here theta minus 90 degrees, and we can calculate this and this using this hypotenuse of 1, and we can find the new values, the redefined values of sin theta and cosine theta. So now we have abstracted away from the triangle, we have converted sin theta and cosine theta to coordinates on a circle instead. So now that we've done this, we do not have the limitation of only being able to solve for theta between 0 and 90 degrees. We can now solve for any theta in the real numbers, because we can rotate as many times as we want in the clockwise direction in order to get to a certain direction, or we can rotate as many times as we want in the anti-clockwise direction to get to a certain direction. Remember, an angle is just how much you rotate to be facing one direction, starting from facing a different direction. So if I start from facing the positive x direction, I can rotate this much to face into this direction, or I could rotate this much into facing this direction, or I could do a couple of turns around the circle and then do that, and it'll all be the exact same thing. So now that we have redefined sin theta and cosine theta based on a circle instead of a triangle, we do not have the limitation of theta between 0 and 90 anymore. Now considering this circle was the unit circle, it had radius 1. So considering where we are on a point on the circle. This circle is defined by the equation x² plus y² is equal to 1. That's simply the equation of the circle. The circle is the collection of all points x, y that satisfy the equation x² plus y² equals 1 within the real numbers. So then, what is x and what is y here? Well, this coordinate here is one of the points on the circle. So certainly, this point must satisfy the equation x² plus y² is equal to 1. The x coordinate here is cosine theta, and the y coordinate here is sin theta. So we can write the x coordinate in this particular case is cosine theta, and the y coordinate in this particular case is sin theta. So certainly, if this point cosine theta comma sin theta is on the circle, it satisfies the equation x² plus y² equal to 1. So therefore, substituting x equals cosine theta and y equals sin theta into the above, we can see that cosine theta squared plus sin theta squared is equal to 1, meaning that cosine square theta, note that this is a change of notation, we write cosine theta squared as cosine square theta plus sin square theta is equal to 1. Hence, we have shown that cosine square theta plus sin square theta is equal to 1. So for this, we had the prerequisite of knowing the equation of a circle. The circle is x² plus y² is equal to the radius squared. We had to know this. There's no real easy way to argue how you would have to know this, other than saying any coordinate on the circle would be a distance of x in some direction of the x-axis away from the circle, and a certain other distance y away from the center of the circle. So that is the definition of the coordinate. So the coordinates of the circle would be such that we have a right angle triangle where we have x distance away from the center of the circle and a y distance away from the center of the circle. So then, by the Pythagorean theorem, whatever x distance we travelled squared plus whatever y distance we travelled squared has to be equal to the radius of the circle, this hypotenuse of this 90-degree triangle that we've constructed away from the center. Similarly here, we have the same exact property. We are moving a certain distance away from the center of the circle, and in a perpendicular distance another distance away from the center of the circle. So then, the square of these two distances must be equal to the square of the radius in order for us to be that given distance away from the center of the circle. So the definition of this equation, the equation of a circle, is reliant on our knowledge that the distance of a point away from another point, let's instead of OA I'll write AB, the distance of one point away from another point is the square root of the difference of their coordinates, which I'll write as x2 minus x1 squared, plus the difference of their y coordinates, which is y2 minus y1 squared. Recall this from our previous lesson on Cartesian geometry. So I hope no one has any confusion on how I got to this answer, how I got x squared plus y squared is equal to 1. It's by the definition of a circle, which itself is coming from the definition of the distance between 2 points within a Cartesian coordinate system. So I mentioned all of that simply because someone might have a doubt on how I first immediately said that x squared plus y squared has to be equal to 1 for this circle. It's because the circle is defined as the point, all the points which are a distance of radius r away from a certain center, which in this case was the origin, and the distance of a point away from the origin or some other point is given by this equation here. I hope that alleviates any confusion that someone might have with this proof. I hope no one has any issues with this proof. So that is it for this proof then. Thank you for watching and goodbye.